Okay, can I have your attention, please? All right. Today is February 24th. We are doing time complexity searching and sorting. Our next class will be a review. Yay. And that's, please bring all your questions. Please stump the professor. You know, that's the game we're going to play. So please make sure you do that. And then on the 28th, we will have our midterm. Yay. And then we have our Mardi Gras break. Mardi Gras break will include for this class the lecture on Friday. In addition, there will be a final project step due on that Friday. But I will not be at that lab because I will be at Disney World. But I'll be at other labs. So if you have a question, you know, try and get it in early. Also, I'm going to move my office hour. I have my office hour listed as 12:30 today. I'm going to move it to 1 o'clock because it turns out that whenever I go to lunch, I have trouble getting back on time. So I don't think it's mattered too much. People rarely ever come to my office hours, but and this is something that puzzles me, by the way. And here's the other thing about it, right? The only people who ever come to my office hours are people who are doing well, right? Like I remember last semester, I had this one kid show up at my office hours. He says, all right, I'm here to talk about my grade. I'm worried about my grade. And I look it up. He's got a B+. And I'm thinking, all the students that's failing, and the one that shows up who's concerned about his grade is one who's getting a B+. Anyway, so I'm going to have office hours at 1 o'clock today and 1 o'clock from now on. As I say, final project part 2, actually. Part 0 is the 100 lines. Will be 400 lines on Friday of this week. Sorry, next week. Friday of next week. This week we've got, what do we have for a lab? We have our sorting lab. All right. Any questions on what we're going to be doing? And remember, you can always consult this syllabus yourself. It's linked right off the homepage, and you can always see what we're going to do every day from now until the end of the course. No questions. All right. So let's go back to where we left off. All right, we were talking about sorting, searching in Big O. Right, we were just starting to talk about, we just been talking about this stuff. We've been talking about how to compare, right? And this was our comparison routine, right? And it shows how you implement a compare, right? That was the thing that we were doing there. And interesting. Okay. I didn't know it would go into that mode. Okay, and what we looked at last time was we looked at mergesorter.o, right? And what we found was there was only one thing that really changed, and this was this line right here, right? What we did was we took out our less than or equal to, and we replaced it with this function call, and now it will work for practically any object, so long as that object implements comparable. And most of the standard objects will do that. You know, all the wrapper types, integer, double, character, they'll all implement that, and string as well. That will implement that. So you can sort anything with that. And we did an example of sorting anything with that down below. We sorted this array of strings and this array of integers with the same sorter. Any questions about any of that? Yes. Is it JJ? Yes. Okay. All the basic objects are automatically used with comparables. So if I create a class, does not automatically use comparables? No, you have to. If you create a class, Okay, so the question is, all the basic types have comparable. Does that happen with the classes you create? No, you have to explicitly implement comparable in order for that to work. And we're going to take an example. We're going to do an example of that in a minute. Okay, so all right. So let's look at the quick sorter. So the quick sorter is going to, this is the wrong code. Oh no, it's the right code. I just didn't update it the way I wanted to. Ah. All right, let's change this. All right. Hold on. Yeah, all right. We're gonna create quick sorter 2 O2 is that what we're gonna do. And so what I'm doing is I'm taking the integer version and I'm gonna replace this with comparable. And I'm gonna replace this with comparable. And I'm gonna replace that's nice and loud, huh? Let's turn that down. Okay, so what I did, I changed the pivot value to comparable and I added something else, and that was an int and I named it 0. And you're probably wondering why I did that. And I'm going to show you in a minute. Okay, so what is our rule for doing this, right? We're gonna partition, we're gonna say, this is a less than, so we're gonna change it to compare to less than 0. And I used the 0 that I defined, that I passed as an argument rather than the actual number 0. And then this is a greater than or equal to dot compare to and this one, I really don't need this check because if it's gotten past the other two, that's automatically true. So I'm just going to keep it like this. I'm not going to replace that third one. And this code, I'll put this code on the slides and on the website and everything. So don't worry about that. And then this needs to change to comparable. And now here's the thing. Comparable. Now here's the place where the 0 comes in, right? Because what I did when I was sorting the integers was I compared to pivot val plus 1, right? And comparable is not something that I can add 1 to, right? It just doesn't work that way. So what I'm going to do instead, right, is I'm going to put a 0 here and a 1 there. And so now my value for 0 is 1. And what that means is that when I go and compare for less than 0, I'm really comparing for less than or equal to 0. Okay, when I compare for greater than or equal to 0, I'm greater than or equal to 1. There's probably a better name for 0. I mean, I guess what I should call it, because it's really awful programming to call something 0 and then pass a 1. So I shouldn't do that. Let me, because it's confusing, right? So what I'm going to do instead, I'm going to give it a longer name. I'm going to call it 0 or 1. All right, I feel better about myself now. I don't know how you feel about me, but I feel better about myself for having done that. Yes. Oh, yes, I did. You know, I don't have a whole lot of memories of professors talking to me from high school, but I remember this high school physics lecture. The guy was up at the board and he was doing, some kind of projectile tracing a parabola, and he's solving the equations. And he says, all right, and here we take the square root of -4 and we get what? -2. And me and the guy sitting next to me look at each other like, what? and then in this next step, he does this other thing. We divide by 0 and we get what? 0. And we look at each other again. He got the right answer. Like those two mistakes canceled each other out. And so we said nothing and we just sort of shook our heads and went about our day. Anyway, just something for your amusement. All right, so 0 or 1. Now, the notion is, right, if I say, if 0 or 1 is equal to 0, that less than on this line will be a less than. But if it's a 1, then it's going to be a less than or equal to. You see that? Does that make sense? Do you have a question? Yes, JJ. What is a pivot value? Okay, so let's remind ourselves how quicksort works. The way quicksort works is it's an algorithm that's special. One of the things I like about it is it's an algorithm that requires a random number to work properly. And I think that's cool. So what we do is we use this little bit of math here. We say int n equal n minus start. If n is less than 2, that means that's our bailout condition. That means that we have one or 0 elements in our array, and there's nothing to worry about. And then ran.nextInt is going to give us something in the range of end minus start. So if I add start to that, that gives me something in the range start to end. And then what I'm going to do is I'm going to take the pivot value, which is the value at that random index. And now I'm going to sort things into 3 piles: less than the pivot value, equal to the pivot value, and greater than the pivot value. And I'm going to do that sorting in place. So they're not going to be distinct piles. I mean, I could write, I could do what I did with merge sorter. I could make 3 arrays, and I could put the less than in the first array, and then the equal in the second array, and then the not and the greater than in the third array. And then at the end, I could refill the arrays from those things. If I did it that way, I would use more memory, but guess what? I would get a stable sort. Anyway, and you remember what a stable sort is, right? Okay. All right. I saw heads nodding. Anybody not remember what a stable sort is? Okay, there's some of you that don't remember. Okay, so the notion of an unstable sort means that if I have things that are equal, they might get shuffled around during the sorting process. And if you want to think about this, think about your spreadsheets, right? When you're sorting first by somebody's last name and then by somebody's first name, you don't expect that people with the same first name will now have their last name scrambled in the order in the spreadsheet. But that's what a quicksort will do. It will potentially scramble those things, whereas a merge sort will keep them in order. So the stability of the sort is about what happens to the objects that are considered equal. And I think this will make a little more sense to you once we talk about how to implement comparable. Okay, so, all right. So I have to just sort into my 3 piles, and this is the way I convince my generic comparable sort to do that. And if I've done everything correctly, this code should just work. So what I'm going to do, is I'm going to go into my merge sorter routine code. My computer apparently decides it needs coffee or something. All right, we're going to take this code. And we're going to put it here. And then we're going to change quick sorter O2, quick sorter O2. All right. And then Let's see if this compiles. Nope. 17. Every so often my computer gets into this mode where it wants to be really slow about everything. I don't understand quite why. Oh, yeah, well, of course. All right. I had two else's in a row. You can't do that, obviously. And I didn't remember to change the class name to match the source file. All right. It looks like I missed a type. Line 16. Swap. Oh, swap. Right. Because I'm extending sorter. And I am no longer doing that. Void swap. Comparable array int I1, int I2. Comparable temp equal array I1. One. Okay, let's see how that goes. Rand, okay. I really wish that like I could give you coding problems and a compiler and have you not give you access to the internet and AI and chats and so forth, instead of just bubble sheets. I wish I could do that. Maybe someday it'll be possible. Non-static methods sort. Okay. So I previously was implementing the sorter so that the sorter in such a way as I could use that generic sorter base class. But now I'm not doing it. Yeah, we got compilation, people. Two, three, four, five, seven, 100, ant, bug, fish, ham, people, rice. It even worked. If you do that much changing to a code, it's a miracle if it works correctly. So you just witnessed a miracle. You should make little medallions for the day and wear them around your neck whenever you code. All right. Any questions about that? Any questions about how to make quick sorter a generic code? Yes, Olivia. What was all that fixing I did? Okay, so I was hoping you'd sort of follow along as I was doing it, but let's review it a bit. So actually, let me do it this way. I'll try to make my screen a little wider. vdiff. Quick. I don't know if this will look okay. Let's just try it out. Okay, so this is a diff of the two codes, the one I started with and the one I ended up with. Now, in my quick sorter 2, I had to declare random because I was getting random by inheritance from the sorter base class, and I'm no longer extending sorter. So I had to get my own rand variable, and I had to make my own swap routine. And I needed my own swap routine because it's a different type. The base class was using an integer array, and I now need a comparable array. Good with me so far? All right. So then I had to go and I had to stick static on everything because I'm just not using it the same way. And sorting doesn't require any state in the class inherently. So I'm going with that. Just adding that. Now, the next changes that I make, right? I am just replacing int in the relevant places with comparable. So there are places where I want the int still because they're indexes, right? They're not the type of the thing I'm sorting. They're just an index into that array, and that stays an int. But everything that refers to an array element, like this temporary variable in the swap above here, these all have to change to be the right type. So that's mostly what I was doing, was changing the type. Now, the other thing that changes, right, is this pivot comparison. So every time I have a less than, I now have to replace that with a compare to. And I used a 0 or 1 as my target. Now, normally you would put just a 0 there. But in this case, I'm thinking ahead, right? And I know that when I partition, I have to partition twice. And I want to partition by less than and by less than or equal. And I can't do it the easy way that I did in Quicksorter 2. I can't add 1 to my value because comparable does not support adding 1. It's not necessarily an integer. It might be a string, right? I can't just add 1 to a string. So in this case, what I had to do was I had to make this additional argument 0 or 1 and pass it along to my comparison routines. Are we good with that? I think that's the trickiest step. Okay. And then the remainder of it is just changing the types, right? Really. So I go, I need the array, this array to become comparable. I need the pivot value to be comparable. And then my two calls to partition take a 0 or a 1 at the last argument, depending on which stage of the partitioning I'm in. And note, when I do this partitioning the second time, I'm passing I1 as the start of the array. So I'm not trying to partition the stuff I've already successfully partitioned as less than. Okay. And that applies to both of them. And then I just copied the main routine from my merge sorter O and changed the name from merge sorter O to quick sorter O2, just as to provide a test for my quick sorter. All right. Everybody happy? Everybody who's dazed and confused? You have a question? No, you okay. Well, do you have like one particular place that stands out as problematic? The last part where I put the main routine? That doesn't seem like what you meant. If anything is going to give people trouble. Yeah, so comparable, right, is I just have to replace less than is supported for integer types, right? But it's not supported for strings or anything else. So I need to use a special interface for that to come up with that. I need comparable. I need to call a method compare to, and we've talked about how to make that transformation. And so that's all I'm doing here is I'm transforming to make this a generic thing to work with an object. I'm changing the less thans to compare tos and the greater than or equals to compare tos. And normally I can just put 0 on the right-hand side, but this is kind of a special case. All right. Did that help at all? Okay. All right. So now what I'd like to look at is a code called Rocket. Now, Rocket is just a random class that I made up. And it's got, the rockets have sizes and they have names, so like everybody knows, the SpaceX rocket, the Starship is the biggest one, that's ever been made, and so on. So that's kind of what I was thinking about. And so what I did with this class is I put this integer size and the string name on it, and I had it implement comparable, right? And now that means I have to write a compare to method. Now, in my compare to method, the first thing I'm going to do, it's going to take an object O, because this sort of generic means that I'm working with a generic object, but I really am not, right? When I do a compare to, I'm only going to be comparing with other rockets. So I'm just going to cast it to Rocket. And yes, that is unsafe. If I pass something that isn't a rocket to this compare to method, my code will die with a class cast exception. But I'm just gonna say, if that happens, the code deserves to die because that's an error, right? So it depends on your needs, but in my case, that's what I'm going to say. So I always like to call, when I'm doing a compare to, I always like to call the variable that I'm casting to that, because keyword this is already present for the current object, and I have this like cute little thing. I can compare this to that, right? So it sort of makes sense linguistically. All right, and I'm going to show you. I structure the code in a way that I think is kind of formulaic, which allows you to possibly implement your own more easily. So my formulaic way to do this is I put my difference as a variable, and I set it to 0 to start off with. And I say if diff is equal to 0. Now at this stage, of course, diff is guaranteed to be 0, but I'm just sort of being formulaic about it, as I told you. So I'm saying if diff is equal to 0, then I'm going to say diff is this dot size minus that dot size. And if it's not, so what I'm doing is I'm comparing first by size, right? I'm comparing first by size. And if the sizes are equal, then this diff will be equal. And only if the sizes are equal will I now compare by name. And I have a string comparison routine that I wrote, and I'm going to talk about that in a minute. But first, I'm just going to say what I could have done here, what I normally do. Somebody in my last time I did this asked me a question, so I could say this dot name dot compare to that dot name. That would be the normal way to write this, right? So that would be the normal way that I would compare this to that. When I want to do size first and then sort by name. That make sense? Does it not? Does somebody have a question about that? All right. And as many things as I want to add to this list of criteria for comparing, first name, last name, age, social security number, whatever, I can just keep adding to that list with that if diff equal thing, formula that I have, right? And it will compare them in that order. And then in the end, I can return diff. And that will tell my sorting routine which things come before which other things. And so now I can, because I've done this, I can now sort a list of rockets. And I've got, these are my various rockets that I put in here, and I'm going to use merge sorter O on them. And you can see that I've sorted them first by size and then by name. So the only two that have the same name are the Falcon Heavy, or the same size, are the Falcon Heavy and the Saturn V, and they got the Falcon Heavy first. Does that make sense? Now, if I want to sort things differently, I can. I can just change the sign of what I'm doing. So if I want to reverse that sort, the easy way to do it is I could return a minus there, right? And now I'm going to sort in the reverse direction. Right now it puts the biggest ones first instead of the smallest ones. So you can get any kind of behavior from the sorting that you want, depending on how you write that compare to method. Make sense? All right. All right, now I'd like to change gears a little bit. Because if I recall correctly, I got one more class on this, right? No, wait a minute. Today is right. No, I got review next class. So let's change gears. Let's go to the next slide. And let's look at the searchers, okay? So I have a generic searcher that I wrote. It's an abstract class, just like the sorter that I wrote. And it's got some of the same properties. It's got this public final static random thing, just like the other one. It's got a create method to create an array of integers. It's got a print method to print an array of integers, and it can take a start and an end. So you can print a subarray. And it's got an abstract method called search this time instead of sort. And then it's got some other reflection code and some timing code and such things. And what I'm going to do is I'm going to implement linear searcher. And linear searcher is possibly the easiest piece of code you will see in this entire course. So what I'm doing is I'm searching in an array for a value, and I want to return the index of the array. And I just have one for loop. I go item by item until I find the thing that I'm looking for, and then I return I. And if I don't find it, I return -1. Hopefully this did not lose you. If it did, worry. Okay. So here's the linear searcher. And above I say time complexity order n. Now I hope that's clear that this should be order n, right? What happened was I went through the array. On average, I'm going to go halfway through the array and return it. It'll take n/2 times to get there, and n/2 iterations on average to get there. So that's order n. Does that make sense to everybody? Okay, it's perfectly understandable, I think. And I suggested to myself that I run it this way, but I can't select. So that's a million zeros, right? That's a 6 zeros, right? All right. Java searcher, linear searcher, 1, 2, 3, 4, 5, 6, 100. Okay, so it took however long it took. I think I need to make it work a little harder. See, the problem here, if I have the way this number is coming out, it's essentially 0. Let's make it 10 times bigger. Right, because if my standard deviation is actually bigger than the time that I get, then it's indistinguishable from 0. Now at least it's not this. Now at least we can tell that it's bigger than 0. Okay. All right. So that's that one. Let's take a look at binary searcher. Okay, so here is my code. Well, you don't understand. We haven't done try catch yet, so you don't need to care about that. That's just making sure assertions are enabled. So the way this routine, this is the way the binary searcher routine is going to work, is I'm going to take an array and I'm going to assume that the array is already sorted. Okay, that's a key assumption in the binary searcher, is we have a sorted array. And what we're going to do is we're going to look at the middle of the array first. And if for the value that we're looking for, and if the value at the middle of the array, right, is less than the value that I'm looking for, then I'm only going to search the upper half of the array. And if it's less than the value I'm looking for, I'm only going to search the lower half of the array. And then I'm going to take that new subarray and I'm going to do the same thing recursively, right? Well, I'm not going to do it. I'm not literally going to do it recursively. I'm going to do it iteratively in this case. I have a while loop. But I'm just going to keep chopping down the array step by step until I get to the value I want. Now, the cool thing about that is that it is order log n, right? And you can see that because each step of my search, I'm cutting away half the remaining values, right? And so it's order log n to get to my value instead of order n. This is much faster than log n is much faster than n. And it will find the answer much quicker. But the caveat, as I said, is that I have to have a sorted array. right? So everything in computer science is a trade-off. This is a much faster way to search for something, but it does require you to have a sorted array. And the sorting takes how much time? N log n, right? So if you first sort something and then do this, it's actually slower than linear search because you had to pay n log n to do it. But if you're going to do this kind of search a bunch of times, more than n, right? If you do n squared searches, then this is a clear win. Any questions? All right. So the way we do this, right, is we're going to take a high and a low value. We're going to set the low to 0 and high to array length -1. And if and then we're going to calculate the midpoint. And we've done this calculation before, right? The midpoint can either be this math or this math. But the point is, I mean, this is the sort of the simplest form of the math, right? Low plus high over 2. It's not high minus low. It's low plus high. We have the high minus low over here, but that's only okay because we're adding low to it. So, right. So algebraically, these two things are the same. And I'm making a big deal out of this because I may make a quiz question out of it. And I also, there's a textbook that I use for parallel programming, which has a merge sort routine, and they put a minus sign in here. And I was copying the code out of the book, and I was trying to make it work. I said, "What the heck is wrong? Why can't I get a simple sort routine to work?" And then it finally dawned on me, that's a minus. It should be a plus, right? So these are the kinds of details you need to pay attention to, and if you don't, you spend hours of time debugging. And oh, by the way, I have a link that I added to the main page about using AI in programming. And I know that's the way forward, right? And people can be faster when they're coding using AI. But there is a trade-off that you're making when you do it. And the article, I think, does a nice job of talking about that. So please take a look at that. There's just a link on the main page. All right. So anyway, I'm going to calculate my midpoint, and then I'm going to do a diff. I'm going to say the array at the midpoint minus the value that I'm looking for. And then I have this verbose flag. And if it's on, it's going to tell me what step I'm on, what the low and high are on, what the midpoint is, what the difference is. It's going to show very detailed, what's going on. And if the diff is 0, then I'm done, right? And if the diff is less, then I'm going to search the upper half of the array. I'm going to replace low with the midpoint +1. So I know that the value at the midpoint isn't what I want. I want +1 to the end. And likewise, if it's greater than, so that's the only other option, right? Equal, less than, this is greater than, I'm going to want to change the high to the mid -1. And at each step, I'm going to print out what I'm doing. And if this doesn't give me the answer at the end, if I don't ever get to this step, then I just return -1. And then I create a random list of things, and I call the binary searcher on it and show the answer. And if I do that, well, if I do this, right, we saw how long that took. And this takes much less than that, like 1,000 times less in this case. And if I run it standalone, right, I have a main method. Right, so there I created an array of 10 things that go 0 to 9, and I'm looking for a value 3, right? And so first I do this diff, and then I get a new high, and then I have this new high, and I do the diff again, and so on. And you can follow it down each step of the way until you get to the end, until you find 3 minus 3 is equal to 0. And I encourage you to play with this code and make sure you understand how it works, right? I want you to see how a binary searcher does its thing. Make sure you have that firmly in your heads. And of course, you could just take this code and make it work with comparable also, right? I did the minus sign there to do the comparisons. So compared to is essentially like minus, right? Any questions? Yes, Vanek. Well, okay, so the idea is if I want to use comparable, then what I want to do is, come on. So what I need to do is the array needs to be of type comparable, right? So this, instead of an integer array, I need a type comparable. And then this value also needs to be type comparable. And then this just becomes a call to array mid dot compare to val, right? Because compare to is kind of like minus, as we discussed. And then the rest of the code just flows from there, right? Nothing else needs to change, I think. Yes, Olivia. Well, okay, so I'll try to explain this visually. So 0, 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, right? So if I'm searching for a 3, I start here, right? I'm starting at the midpoint. And when that fails, then I'm going to search the array here, right? I'm going to take just the lower part of it, right? So 4 is not equal to 3, but 4 is also bigger than 3. So I know I want to search the things that are less than, right? Okay, so now this is the array I'm searching, and I want to search the midpoint. And I think if I just do the math, I'm going to wind up there. Hold on. Yeah, that's where I wound up. So now I know that I'm greater than that, right? I know that the thing is going to be greater than that. So the next array I'm going to search is going to be 2, 3, right? And when I compute my midpoint, it's going to take me there. And then I know it's going to be greater than that. So it's going to take me there, right? Sorry. And then that's where I am. And I'm done. Make sense? Yes. What's your name?
Malik.
Malik.
Does it not check the high and low points? Like, would it not have noticed the 3 after the second step?
No, it wouldn't know that because it has to do a comparison to know if it's equal, right? It knows that it's, I mean, yes, the problem is you have to not think like a human, right? A human looks at the array and we say, well, the 3 is right there, right? Because what our brain has somehow done this algorithm in some subconscious way, and it just seems obvious to us. But you have to not do that. You have to think very methodically, how do I know? And so what you're doing is imagine that instead of having all these numbers here where you can see them, right? Imagine that instead what you have is a set of cards that are just laying face down and you can't see what they are. Right? So what I'm really doing is I'm going in here and I'm looking at this one and I'm saying, I have a 3. What do you have? And it's a 4. Okay, and now I know that my next subarray is going to just be these pieces. And I've got to pick one to flip over, right? And what I'm going to do is I'm going to flip over this one, and it's going to turn out to be 1. And then I've got this array, and I'm going to flip this one over, and it's going to be 2. And then I'm going to say, well, I've got one more chance, and sure enough, it's 3. Okay, so that's sort of looking at it from a computer's perspective. Right, the computer sees these as face down cards, and I have to turn them over by comparing. Make sense? All right. Who has a question about this? Yes, Michael. Yes.
Because it's a with the integer, you just drop the zeros.
Yes. So the way Java works, and hopefully you learned this last semester. Integer math, you round down. You know, I had the oops. I had this when I was a graduate student. I had this program. I was using Mathematica. I told Mathematica to generate Fortran code for me from this expression that it figured out, and my code just wasn't working. It was giving me the wrong answers, and it struggled and struggled. And then I noticed that it had written expressions like a star star, which is how you write exponentiation in Fortran. It said a star star parentheses 1/2. And to the human eye, that looks like a half, and that looks like a square root. But what Fortran does is it does integer math, just like Java. 1/2 is 0. So it was raising everything to the 0 power, not the 1/2 power. And I had to go into my code and put decimal points on there because 1.0 over 2.0 is 0.5, but 1/2 is 0. All right. Any other questions? All right. I think that's enough for today. Next class, we're doing a review, and then we're having a midterm. Yay! You should be.